right, everyone, welcome back. Let's talk about Chapter 32, the last of the chapters that I was dealing with regarding the Halliday and Resnick 10th edition book. So Chapter 32 from Halliday and Resnick, 10th edition, pertains to Maxwell's equations and the magnetism of matter. So Maxwell's equations, magnetism of matter. Problems 12 and 29 are what I'm going to try to do. So let's take a look. For problem number 12, a parallel plate capacitor with circular plates of radius 40 millimeters is being discharged by a current of 6 amps. At what radius, A, inside, and B, outside the capacitor gap, is the magnitude of the induced magnetic field equal to 75% of its maximum value? C, what is that maximum value? So let's take a look at it. Let's write a couple general things down and we'll see what we can say. We are aware of this, and we're also aware in a special case scenario, such as what we're in actually, in this problem, this is d phi sub E. The rate of change in flux of the electric field for this problem. In a more general sense, they kind of write this in a little more general way, I guess you could say. And that is, they write it as, okay, I got this here, guys. We already have it. You know what I'm talking about. So let me get rid of this. And we said, like in a general sense, this thing right here is kind of a special case of a more general phenomenon that is discussed and written down mathematically. The changing flux of the changing flux of the electric field behaves like a current, or has elements of its behavior. It's like a fictitious current. It has elements of behaving like a current. And that's why a more general sense of this, and this is also changing, dealing with the rate of change of the electric flux, they write it like this. We've got that. Whereas the displacement current, that fictitious current, is equal to this right here. So I sub d and so on and so forth. So how are we gonna answer the question that they're asking here? Again, let's ask it. I mean, it's worthwhile. They're saying a parallel plate capacitor with circular plates of radius 40 millimeters is being discharged by a current of 6 amps. At what radius, A, inside, and B, outside the capacitor gap, is the magnitude of the induced magnetic field equal to 75% of its maximum value? C, what is that maximum value? Okay, So let's just run through it. You're looking at something like this, and okay, and we can come back. Now we're not worried about between the plates. There's no real current enclosed between the plates, so this kind of falls out of there, and you just got this and that, and that's what we had over here. So let's keep going in that direction. A little bit of repetition on the whole matter, but we follow follow Ampere's law, and generally the laws of electricity and magnetism that are going on. We're following all those as carefully as we can. True. This right here, there's a number of ways we can write it. As this is going, that's B 2 pi r. As the dot product goes, and this is just all the way circling. You can be, the B vector is going to be a constant. If it's a constant, this whole thing's going to be a scalar. The B vector is, the B vector is always in line with the path, the circular path that is being taken as we do the integration. There's a circular path taken in the integration, and there's a circular path associated with the B vector. The B vector and delta S vector, as we proceed around, are always in line with one another. There's a degree measurement of 0 degrees or 0 radians between both. So when you do the dot product, is just B times ds, and you're integrating the ds because the B is a constant. So it comes down to here. D phi we get to here, and yeah, because E times A is, E times A, it's a constant E field, or is it? That's another point here. I don't want to, no, I take that back. I'm not saying it's a constant E field. We just know that it's this, and then the E field itself, the A is constant, the E field will not be. So when you do this, you're basically getting down to, there's a whole bunch you can say, and it's not too complicated, but I just don't want to be careful. You don't want to make a careless error with some of this stuff. We see that can happen. A is a constant. Bring it out. There's a varying E field. Fantastic. So if that's the case, it's kind of a general look at what's going on here. Now, we've got this. So let's see here. When capital, all right, guys, let's just erase a few things. Still on problem 12, obviously. All right, what's going on here, guys? Well, you got an answer here, and they're kind of asking you how to play this. Well, when R, there's going to be two scenarios. When the radius under consideration inside of the capacitor, you're not exceeding the capacitor radius, you're less than or equal to the capacitor radius, you got this. If that's the case, you're not exceeding the capacitor radius, so the area under consideration for the flux is the area of the area that is enclosed within the capacitor plate. That will be pi r squared. So basically for this situation, you're dividing by 2 pi r, and you got mu 0 epsilon naught A over dE dt over 2 pi r. Right, true. So if that, let's let it be at that. Let's kind of stay there and kind of talk a little bit. For inside the capacitor plate, the area is pi small r squared. So it becomes B equals mu 0 epsilon naught pi r squared dE dt. What do we got? Pi and pi cancel. R squared and r cancel. You got an r right here. You've got, for this guy, for the less than scenario, you've got mu 0 epsilon naught r over 2, yeah, mu 0 epsilon naught r over 2 dE dt. Yeah, true. The other scenario is when R exceeds the area. Well, the flux, nothing's going on the outside of that, so the flux cannot exceed something associated with the maximum area that's allowed. So right here, for the other scenario, for R greater than or equal to capital R, you're going to get a situation over 2 pi small r. Well, the small r happens to be a radius that's bigger than the big R, actually. So it's a little, watch out, It's just that the letter is small r, but it's actually, for the outside, it's greater than or equal to. So it could be as big as capital R or bigger than capital R. But here it is. The 2 stays, the pi's go, the r squared goes. The r squared has to stay as is, and you got the r. So what you got here is dE dt. So there it is. Absolutely. I mean, so this is the situation. Now look, they're going to be the same answer if r is less than or equal, if small r is less than or equal to, if small r is less than or equal to big R, and we actually said that the small r and the big R are equal, and here small r is greater than or equal to big R, if small r is equal to big R, it does work out. If small r is equal to big R, small r is equal to big R, in other words, in place of big R, put a small r right here. Small r squared, r into small r squared is just small r. It's mu 0 epsilon naught small r over 2. Wait a minute, that's the same as this. Mu 0 epsilon naught small r over 2. You know, if you were to put, time out. Shouldn't have said the small r. Let's make small r equal to big R. If small r is equal to big R, in this with the same reality going on here, let's just go to the equal. Small r is equal to big R. Small r equals big R. Small r equals big R. Big R right here. Big R goes into big R squared. Big R times. It's mu 0 epsilon naught big R over 2. Really? If small r is equal to big R, put a big R right here, it's mu 0 epsilon naught big R over 2 times dE dt times dE dt over here. I didn't say that last time. But they do correspond. These are set up in such a way that they will connect when small r equals big R. The equations actually work. From there, it's the only thing you have to worry about. Where this is happening, how this works, and what the value is. All right, so let's take a look at it. All right, we've said a lot. You can always go back with the film and keep this under control, guys, and always keep tabs of what we've done in the past. Obviously, that's always the procedure that the film affords us. So let's see what we can say. Let's compare. Let's find out where that R would be. We want 75% of the max, whatever that max may happen to be. 75% of the max compared to the actual max. Bmax divided by Bmax is 0.75. 0.75 over 1, or just 0.75. We know the maximum value. The maximum value, we already we did the whole song and dance over there. I said the max is going to occur, or at least we feel that it's going to occur, when the biggest value is going to be. Going to be in circumstances such as this. Let's see here now for the big stuff here. Yeah, the biggest it can be over here. It's got to be. It's kind of pinned right here how big it can go, and we found the biggest that it could be was what we just said in a verbal sense, guys. And let's just set small r equal to big R, and we were able to find this. I don't know, I think I got enough parentheses now, right? We probably don't need that many parentheses, but there it is. And the other one is, from the inside now. So what inside value? Well, the inside value is according to this formula. The max is when small r equals big R. When small r equals big R, when small r equals big R, we got this bottom one. So that was the max right here. 75% of that would be, I guess there is a mu 0 epsilon naught R1 over 2 dE dt. Well, okay. dE dt, dE dt, gone. The 2's, you know, the 2 flips upside down and the 2's cancel. The mu 0, epsilon naught, epsilon naught. You got R1 over big R. You've got 0.75 over 1 equals R1 over big R. The small multiplied by capital R on each side. There's your answer. The big radius is 44 millimeters. 44 millimeters times 0.75 is 30 millimeters. And that's R1. That's A. B, where would the outside happen? You know, in what circumstances would you get the outside guy to be working like that? Well, look, I went value on inside divided by max. Value on inside, a particular value on the inside, divided by the max will give me 0.75, and we solved it. Now we're going to take a value on the outside divided by the same max, and can that also give us 0.75, and can we solve it? All right, so for this one, we're doing the same thing. It's going to be this. These cancel. You get this. Now I'm going to go for some outside thing. Well, the outside thing is a phenomenon looking like that's the inside. So this pertains to inside. This pertains to outside. So we dealt with the inside earlier, inside over the max, over the absolute max, various levels of various values of B that we can find on the inside divided by the max. Now we're going to find various levels of B on the outside divided by the same max. So this is the outside, that's what we're going to use. So it's going to be outside over the max. The outside is over 2R. Well, let's call that R sub 2. It's got to be some number. They got this. And the other one is what the max was. And we said the max was going to be right at the edge. And in all circumstances, it's this. True. That's out of there. The 2's are out of there. Let's make sure I've got this. Right, that's the max. That's this. Yeah, it's looking about right. Yeah, it's looking pretty good. I mean, you got the 2's right here. Mu 0, epsilon naught. What do we got? We got big R squared over R sub 2 divided by big R. At the end, that's just big R over R sub 2. So what we have here is we got 0.75 over 1. 0.75 over 1 is just 0.75. And it's working like this. It's a little different dynamic. But that's a pretty important place to reach. Because now we're just a stone's throw away from actually solving this whole thing. Well, I'll tell you what. Let's multiply by R sub 2. Let's multiply by R sub 2 on each side and divide by 0.75. And R sub 2 equals big R divided by 0.75. Big R is 40 millimeters. Big R is 40 millimeters divided by 0.75 is 53.3 repeating millimeters. Yeah, it's outside of the 40 millimeter place that we were talking about. Absolutely. That's A. B, R sub 2 is 53.3 millimeters. 53.33 millimeters. What's C? What is that max? Well, that max is something we just plug in and go for it. We knew the max from the very get-go was going to be all this bottom stuff right here. The max B max was mu 0 epsilon naught capital R over 2 dE dt. Well, let's give ourselves a little more room, and we can talk about it a little bit. But okay. Yeah, I mean, we came to the conclusion, or at least we pointed to where the conclusion was going to be. There's a number of ways to go here, I guess you could say. Let's remember where we were. What was the max? Well, the max was going to be, the max is going to correspond to there being capital R equals capital R. Small r equals capital R. Put it here, you get mu 0 epsilon naught. Put a capital R right here. Mu 0 epsilon naught, big R, just to power 1, over 2 d dt. If you don't believe me, go right here. Put capital R right here. Put capital R right there. It's going to be the same answer. So the B max, and that's derivable in its own way. I mean, in a number of ways you can derive that, why that would be the answer. But let's go. Let's take a look at it. B max equals mu 0 epsilon naught capital R over 2 dE dt. Can we get out of this somehow? Well, yeah. The displacement current is going to be the same as the current that's flowing through kind of on the outside, away from the capacitor plates. That's where it's going to play that role. So what you got here is you can kind of write it as. Let's try to write it here in some manner that makes a little bit of sense here. Mu 0 epsilon naught dt. Yeah, right. You guys remember, in a sense, there's kind of an interesting thing that goes on here. Didn't we say something to the effect of dA, maybe a good like kind of gut feeling for some of the stuff that's going on, you guys. dA equals Q over epsilon naught. It's a constant E field. Something like that. And E, this is just A. Well, we've been down this path before. If you take this and multiply by epsilon naught, take what you have right here. Take what you have right here and multiply by epsilon naught on each side. We got epsilon naught EA. Well, epsilon naught and A in these circumstances is a constant. These two are constants. Epsilon naught, epsilon naught and EA. So let me sort of see what we can say here, guys. And we said this dE dt, that's the change in the flux. Okay, let's see what I can say here. That was that, yeah. We could get the time derivative here and get dq dt equals epsilon naught A dE dt. True. The area under consideration is the pi r capital R. So let's see here. This is more like a displacement current, if anything. Just trying to argue with myself where I'd go with this. Yeah, we said it was this. Yeah, let's say it yet another way though, for the heck of it. Maybe get ourselves out of the woods. Did we say that for the max, it's going to be 2 pi capital R on the bottom, right? When we did the earlier work, guys. I'm just trying to go back to that earlier work. Mu 0. Let's have a look. Mu 0 I and see where we had this thing. See, we had said earlier, I mean, we're going, how far back do you want to go? We had said, let's go pretty far back. I mean, we had said something, you saw what I just did right here. Played a little game. I mean, the game was, doing the dot product here. And played this, got it to here, then we got it to here. Then we said, okay, multiply by epsilon naught on each side and get to here. Then go dq dt, which is some kind of a displacement current. It behaves like a current, it's fictitious, but dq dt is some kind of current for our purposes. dq dt is some kind of current for our purposes. And that's given us this. True. Now what? Well, I'll tell you what. I mean, we said it a while back. Let's go back, I guess. We know from a special case of Ampere's law regarding this. Yeah, that is believable because Well, I mean, it's right here. You can come down here, you can stay there. This is phi. This is phi e. Q equals epsilon naught phi e. If you get the derivative with regard to t on each side of this equation, you get I sub d is going to be that dq dt. And do the derivative here, that's equal to d phi epsilon naught dt. Well, wait a minute. That equals this equals this. D phi dt. So in other words, I sub d equals epsilon d phi this dt. Yeah, okay. That's mu. That's I sub d. That's mu 0 I sub d. So what happens is, so all of this is connected, guys. I mean, we can, here I went a little further, but this right here, that right there is d phi sub e dt. That's d phi sub e dt. So don't worry about that. We could have played this a number of ways. The big thing is, can you get, do we believe this? Well, believe all of this, because it's true, it works. Maybe it's a little more streamlined if we just get something like this, do the time derivative. What does that mean? We'll do the time derivative of q. Do the time derivative of the q function, you get I sub d. That's the same, that's a constant, and then this varies somehow. And there you go. Well, yeah, all of that is right here. That's I sub d. This thing right here, the top, the whole song and dance at the end of the whole thing, sum 2 pi r, and that works for all circumstances, The flux varies within, but outside the flux is its own situation under consideration. How much flux is there? Well, so that's not changing too much. It's pi r squared, and we'll see where that thing goes. So this is mu 0 I sub d. B is going to be mu 0 I sub d over 2 pi r. There's a lot that happened, guys. I mean, it's weird how the whole thing is kind of, how it's there. The I sub d, it's discharging with a 6 amp. The 6 amps is the I sub d. The 6 amps that they told us is the I sub d that you're going to put here. Yeah, the I sub d is what you got here. Now, there's a lot happening there, guys. I mean, in the whole process. I mean, we said that B right there, I mean, we just didn't know what dE dt was. We could find out a bunch of things. There's games we can play to talk about the change in the electric flux. That's another problem. But I think this is the thing right here. You've got a mu 0, a constant, a 2, a constant, a pi, a constant, and R right here is where the max would be. And I mean, the way the max would be for something like this, you guys, is essentially, I mean, this is it. And you plug in here, and you find out what the B field is. Plug in all relevant answers. I think the small r you have to use, that's big R rather, I'm sorry. And at big R is what, at R is here, but then you're talking about the maximum, and that's big R right there. Where did that come from? Well, that's the max. And C B max equals mu 0 I sub d over 2 pi capital R. Plug in all the appropriate values, you guys. And we're getting 3 times 10 to the negative 5 Tesla. That's 30 microtesla. Yeah, I mean, that was coming from a number of places, I mean, to make that actually happen. So, you could find a lot. I mean, how the E field's varying, how the flux is varying, the number of ways you can find some stuff out here, guys. And I think the next problem that we're going to do, problem 29, kind of manifests these phenomena pretty well. So we got this. Number of ways to look at it. Like I said, you could have gone with, the 2 pi r, the whole thing right there, right? That's the I sub d. That'll work. The maximum place it's going to happen is this. If it goes more than that, because that's the rate at which the current is going. Now there's less current, less displacement current within a more confined area there. So there's things that would be happening here, guys, to make this happen. It's a lot. There's a lot here. I mean, there's many ways to look at it, and that's perhaps good things to say down the road as well. Some good things to explore down the road. Let's go to 29. They talk about a capacitor with circular plates of radius capital R equals 18.0 centimeters is connected to a source of EMF. E equals E sub m, that means max. E equals E max times the sine of omega t, where E max is 220 volts, omega is 130 radians per second. The maximum value of the displacement current, I sub d, is 7.6 microamps. Neglecting fringing of the electric field at the edges of the plates. A, B, C, D on this one. A, what is the maximum value of the current I in the circuit? B, what is the maximum value of d phi sub E over dt, where phi sub e is the electric flux through the region between the plates. C, what is the separation d between the plates? D, find the maximum value of the magnitude of B vector between the plates at a distance, radius 11.0 centimeters from the center. Remember, the center, the radius, the big radius, capital R, is 18 centimeters. They want you to find the magnitude at a smaller location. Okay. Shouldn't be too bad. It runs pretty fast, you guys. Let's kind of look at it and see where it's going to go. Well, the Imax is kind of interesting. The Imax is I sub d max. The displacement current and the regular current, they behave very similar. So the max of the displacement current equals the max of the current that's flowing outside of the plates of the capacitors. Make a long story short, here's your answer. ID max equals I max. That fictitious current has to be continuous with the other current that's going on. So what other current is going on? Well, the max current that's going on is 7.60 microamps. True. B. They're asking for B. Let's see here. What is the maximum value of d phi sub e dt? Where d phi sub e is the flux. What is the maximum value of d phi sub e dt? Where phi sub e is the electric flux through the region between the plates. We know as a general rule, and we went there, we already did this. We did this in the last problem actually, so I guess it's fortuitous in that sense that it's there. We know that. We just did this in the last problem. We more or less gave an intuitive derivation as to why this is true. We pointed to it. We derived it intuitively, tried to give more of an intuitive look, an intuitive motivation for why that's true. And I think it made pretty good sense, guys. So what does that mean? Well, it just means this. I mean, if you want this to be a max, that right there has got to be a max. Divide by epsilon naught and you're in business. You got d phi e dt max, divide by epsilon naught on each side, and talk about the max each time you're talking. It's looking like that, right? Assuming, I think, like I said, a lot of times I'm taking the calculations from the instructor's solutions manual. 90 to 99% of the time, I'm sure it's going to be fine. So if something off, guys, at least the mathematics is on the mark. All the mathematics is, the non-numeric symbolic mathematics that is taking place is on the mark. Okay, if there's a calculation error, that's serious enough, but it's not due to any faulty mathematics. The big issue is our non-numeric, is our non-explicitly numeric symbolic mathematics on the mark. You know that it is. It's a great book. I mean, we got a lot of good consultation to look at, so we know they know what they're talking about regarding the non-symbolic mathematics, the non-explicitly numeric mathematics, just the symbols, just the non-explicitly numeric symbols. The math is very much on the mark. So we got it. I mean, at the end of the day, looking pretty good. What about C? C, they are saying, what is the separation, small d, between the plates? Good question. I think what you want to look at regarding that is, let's go back to what you know. You know that I sub d, in general, is working along these lines, and how that all proceeds, that's its own matter. But we know that. We said before that phi sub e is EA for our purposes. True. Work it. I sub d, let's do the derivative. We'll say A, we're going to take A to be a constant. Why are we going to take A to be a constant? Because we're talking about the maximum. I'm going to say, hey, look, let's just take a look at this whole system as a parallel plate capacitor, and I'm going to go for the entire size of the parallel plate capacitor. I'm going to go for the full plate above and the full plate below. They're one's on top of the other. I'm going to go that way. So that A is a constant. It's going to be the maximum area where some sort of change in E field is actually taking place. Look, let's make the long story short. You take this guy, bring the A out, you got dE dt, you're right here. True. We know that epsilon naught, here's A, we're taking A as a constant because we're looking at the entire area of one plate, which is the same as the entire area of the other plate. So we got it like that. dE dt is of interest. Well, I'll tell you what, isn't E times D, E times D is equal to the voltage. Therefore, E is voltage divided by D, or potential difference divided by D. What does that mean? That is capital V over D. Definitely true. This D is the derivative. It's not the same as the D here. It's actually a derivative going on here. I don't know if that makes it even more confusing, but it's different than this. It's just the derivative. So when you're looking at something like this, we got this D is the distance. This D, you guys, is the distance between the plates. So it's a 1 over D in here, but it's the distance between the plates, and it's a constant. So what you get is I sub D equals epsilon naught A over D, right? Sure does. That's the capacity. That's formula for capacitance, guys. If we're careful about it. So you brought the 1 over D. You brought the 1 over D out of there because 1 over D is a constant, so it's not going to affect. This is C. This is V, which is Q. Do a time derivative of Q. You do get some kind of a current. This is C. This is V. Get the derivative. If you were going to get the derivative of CV dt, CV is Q. That's some kind of I going on. Yeah, sure makes sense. Sure makes sense. There it is. Well, good. What are we going to say? Well, if I look at this, I guess I got to deal with the maxes. And if that's the case, let's talk about some things that we do know. So I'm going to leave it like that. ID equals epsilon naught A over D, dV dt. That's pretty important. Definitely leaving this one. Now let's got a lot, guys. We got the answers here, okay. Keep forgetting you got the film, so you can always go back. Let me give myself a little bit of room here and we can finish this thing off. Okay, guys, you can always go back. You got the A and the B. Let's talk about the C. Well, I think I can find the max here. There's a lot I can find. Look, we know vis-a-vis C, we know that the electromotive force, the potential difference supplied by this power source, varies sinusoidally, where the max value that it can possibly have is E sub m. And it varies sinusoidally according to this, which means that E is 220. That's the max sine omega t. They already gave us the omega t, but we'll talk about what we got to talk about. So V is indeed the 220 sine omega t. Absolutely it is. So if you take the time derivative of the power source, that's a constant. The derivative of sine is cosine. Use the chain rule. Omega comes out of there too. And you end up getting omega. I mean, you can play this whatever you want to do here. Now remember, the E sub m is 220. I mean, you could stay, I don't know where you go to explicit numeric symbols or stay with non-explicit numeric symbols. The non-explicit numeric symbols tend to have more wide-ranging consequences and tend to give you a good visualization of what's going on, I think. Leave it like this. It doesn't matter. The 220 and the E sub m are the same thing. We'll do the time derivative. Do the time derivative of the potential difference function, which is this. That's a constant. The derivative of sine is cosine. By the chain rule, omega comes out. And what you end up getting is omega EM, right, cosine omega t. True. What does that mean? It means take dv dt, put it right there, and you're in business. Well, dv dt is all this. So basically you got ID equals epsilon naught A over D. See where we are. Right, epsilon naught A over D. Epsilon naught A over, epsilon naught capital A over D. We also got omega. Guys, these are all constants so far. Let me make that subscript a little more explicit. Omega over D cosine omega t. Yeah, fine. Look, let's just get this thing straight. This is true. This is absolutely true, and the D field varies. I'm sorry, the I sub D, the current varies the same way that it's going to vary according to the mathematics that we did with all that they gave us. This is how it varies. Does it have is there a place where it's at its max? Sure there is. ID at its max is, well, it's every single item here, which is a constant. I can't really do much with it. I did work the A to be the maximum area of the entire situation that was present. That's how I was working it. The D is something I got to solve for. If that cosine omega t is 1, there's your max. Absolutely. Solve for D. Multiply by D on each side, divide by ID max. This is the maximum area, plate area that we're talking about. You're not going outside of the plates on this. You're staying within the plates. ID max is the current that they gave you. D equals epsilon naught capital A omega E sub m over ID max. You plug in all the values that they gave you. You're going to have to find that area. It's pi r squared, but they tell you how big what's the maximum radius that you can reach and still be on the plate. Well, it's the radius of the plate. And you go pi r squared. That's going to be pi capital R squared, the omega they gave you, E sub m they gave you, epsilon naught, D you don't know, but you do know ID max. That's going to be equal to what we said in the first case. The ID max would be the whole thing, right? And that was equal to right, ID max was equal to the whole thing, so that's 7.6 microamps, whatever. You plug in all the stuff, guys, that's here. Just go here when you do it. Here you go. Here's your answer. Again, make sure they're doing the calculations right, but everything else is fine. If there's a calculation error that's not good, it's bad, it's still wrong, but at least we know the mathematics that leads to all this. And we got, so when we do something like this, That's 3.39 millimeters, or 3.39 times 10 to the negative 3 meters. That's C. D. Find the maximum value of the magnitude of B vector between the plates at a distance r equals 11.0 centimeters from the center. Remember, capital R is the radius of each plate, which is 18 centimeters. Capital R is 18 centimeters. Small r is 11 centimeters. How do you find it? Well, the displacement current gets smaller if there's less area involved. The displacement current is at its max when the maximum area through which it's moving, through which the flux is going, through which the flux is changing. When the area is at its max, that's when everything else is going to be at its max. Look, let's just, it's easier done than said, guys, and it should come out pretty good, but how do we mean that? Well, we mean this. If it is at its max, they want B field max, right? And they say a bunch of things here, guys. They say for this, they go, okay, I take off on Ampere's law. I think it's called Ampere Maxwell's law. Gotta look it up. Let me just, it's good to know. It's just beautiful math. Yeah, it's a takeoff of the Ampere Maxwell law. Remarkable, just remarkable stuff, guys. Ampere's law manipulated, or at least expanded. You get the Ampere Maxwell law, and that's when you use displacement current and actual real current encircled. Displacement current and real current encircled, and how that all plays out. Just amazing, just fascinating, really. So you do this, and they want it for a particular area. We're saying the B field is going to be constant around that circular movement, and the dot product, the B vector and ds vector are always parallel to one another. So the angle between them is 0 degrees or 0 radians, and the dot product of any two vectors that are 0 degrees apart or 0 radians apart is just the multiplication of the two vectors. Make a long story short, as you're doing that, and if B is a constant, you bring the B out, you've got this. The dot product's not going to be anything to worry about at that point. It's just the measurement all the way around to get all that. And you got mu 0 ID. Well, this right here is 2 pi r for the radius under consideration, and this is B. This is mu 0. And the ID is the max if you have the entire area considered. But this doesn't have the entire. This would be if you had pi capital R squared. Pi capital R squared over pi capital I squared. That's just 1 over, pi capital R squared divided by pi capital R squared is 1. Then you get ID max. True. But that's not what's happening here. What happens here is you got this, which is a smaller area under consideration. So the displacement current won't be as much at the max. But they're asking here, find the maximum value of the magnitude of B vector between the plates at a distance r equals 11 centimeters. That's not the maximum possible for the entire setup. It's the maximum possible for a situation where small r is 11 centimeters from the center. The total distance from the center to the edge, that radius, capital R, is 18 centimeters. We just want the 11. That's why we can't use ID max. We got to use a ratio of these two to get what the max would be at that radius here. Fascinating. Well, what happens is it's mu 0 ID max mu0 ID max, these guys are r squared on top divided by r cubed on the bottom. Remember, the pies will cancel right here. You got small r squared over big R squared. Small r squared over big R squared. R squared over big R squared. Divide by 2 pi r. We got 2 pi r. Aha. Here's a small r. Here's a small r taken to the second power. They cancel, and you got an r right here. At the end of all that, you guys, what's going on here? Well, that's B, and that's B max at R equals 11 centimeters. Equals 0.11 meters. Well, that's kind of a, that's the B max in that circumstance, at that. What is that? That's mu0 ID max, mu0 ID max R over 2 pi over 2 pi r squared. Small r into small r squared is just an r right here, and you got this. That's it. Yeah, absolutely it's that. Plug in all the appropriate values for us to get this right. B max for those circumstances B max for those circumstances B max for those circumstances is 5.16 times 10 to the negative 12 Tesla. As they have it, as they have the answers given there. Now, I don't, like I said, it could, always be checking this stuff. There's nothing wrong with the mathematical logic that brings us. There's nothing wrong with the mathematical logic that brings us to such conclusions. Again, there's nothing wrong, unless anybody can make a mistake, of course, but it's not happening often, guys. I mean, when we're referring to these great books that are here, they do great work. The Halliday and Resnick book is great. Some great explanations as to what's going on. When we're doing all the mathematics, all the non-numeric symbolic mathematics, when we're doing all of that non-numeric symbolic mathematics correctly, these conclusions are they're on the mark. They're good. If there's a calculation error, watch out for that. Don't make the calculation error. Always be checking that. They should be on the mark. On occasion, they can maybe make, I or anyone else can make a calculation error. Be checking on that. But the big thing here is, what's the logic that brings us to where we have to go? Yeah, well, the logic is sound mathematics, and this is sound mathematics. In the end, that's the most important thing, understanding that. However, you also do have to check the work that you're doing, because if you're giving answers on an exam, the bottom line is going to be that answer. So that's important as well. It's a very strong moral victory to know the sound mathematics to get here, but you got to finish it off right. Okay, so I took it on faith how they actually had done it in the instructor's solution manual as far as many of the calculations, and overwhelmingly they're right when they do that. And again, the mathematics that leads up to this, the non-numeric symbolic mathematics that leads up to these things, is spot on, and that's important to us as well. Be checking on things, work hard, you guys. Very much appreciate your time, and take care.